There is a world where the sun burns 3 times brighter than anything you have ever known. A world where morning can melt metal and night can freeze your breath into crystals of ice. A place so close to our star that it completes an entire year in the time it takes you to finish 3 months of your life. Yet somehow, in the darkest corners of this scorched planet, ancient ice has survived for billions of years, hidden in shadows that have never seen a single ray of light. This is Mercury, the smallest planet in our solar system, the closest to the sun, and perhaps the most extreme place you could ever imagine. Most people think of Mercury as just another dot in the sky, a tiny wanderer that appears briefly before sunrise or after sunset, never straying far from the solar horizon. Ancient civilizations called it the messenger of gods. They watched it race across the heavens faster than any other celestial body, appearing and disappearing like a phantom in the twilight. But they had no idea what they were really looking at. Because Mercury is not just a planet, it is a world of contradictions, a place where the rules of comfort and balance do not exist, where one side bakes under temperatures that would vaporize water instantly, while the other side freezes colder than the depths of Antarctica. A world that should be dead, geologically silent, yet shows signs of activity that scientists are still struggling to explain. Imagine standing on Mercury's surface. If you could survive for even a moment, the sun would dominate half your sky, appearing almost 3 times larger than it does from Earth. Its light would be so intense that the ground beneath your feet would glow with heat. The rocks around you would be older than almost anything on Earth, scarred by billions of years of cosmic violence, craters upon craters, stretching to every horizon, no wind, no sound, no atmosphere to carry even a whisper. And yet, beneath your feet, mysteries pulse through the planet's core, and magnetic field that should not exist, and heartbeat in a world that appears frozen in time. Cliffs that stretch for hundreds of miles, evidence that this entire planet once shrank like a drying fruit. Bright patches on the surface that seem to be forming right now, today, as volatile materials escape into the vacuum of space. Mercury is a world that keeps secrets, secrets about how planets form, secrets about what happens when worlds are born too close to their stars, secrets hidden in ice that has somehow survived in the one place in the inner solar system where it should be impossible. Tonight, we are going to visit this extreme world together. We are going to walk through its violent birth, witness its strange dance around the sun, and uncover the mysteries that have puzzled scientists for generations. We are going to discover why this tiny forgotten planet might hold some of the most important clues about our solar system's past, and perhaps about planets orbiting distant stars across the galaxy. Hey guys, tonight we begin with the remarkable story of Mercury, the most extreme planet in our solar system, a world of fire and ice, where the sun looms 3 times larger in the sky, and shadows hold ancient frozen water, from its punishing temperature swings to its mysterious slow dance around the sun. Mercury's story is one of extremes, survival, and cosmic beauty. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And let me know in the comments where you're tuning in from and what time it is for you. It's always fascinating to see who's joining us from around the world. Now, dim the lights, maybe turn on a fan for that soft background hum, get into your blanket, and let's ease into tonight's journey together. Because what we are about to discover is not just the story of a planet, it is the story of survival against impossible odds. It is the story of a world that was nearly destroyed before it even had a chance to exist, a world that lost almost everything, yet somehow became one of the most fascinating laboratories in our entire solar system. But first, we need to understand how Mercury became what it is today. And that story begins 4.5 billion years ago in a cloud of dust and violence where something terrible was about to happen. 4.5 billion years ago, our solar system did not exist, not as we know it now. There was only a massive cloud of gas and dust, slowly spinning in the darkness of space. Hydrogen and helium left over from the Big Bang, mixed with heavier elements forged in the hearts of dying stars that exploded long before our sun was even a dream. Then something triggered the collapse. Perhaps a nearby supernova sent shock waves rippling through the cloud. Perhaps it was just the inexorable pull of gravity, patient and relentless. Whatever the cause, the cloud began to fall inward, spinning faster and faster, heating up as it contracted. At its center, temperatures climbed until hydrogen atoms began to fuse. The sun ignited, and around it, in a disk of leftover material, the planets began to take shape. Mercury formed in the hottest part of this disk, close to the newborn sun. In those early days, the inner solar system was chaos. Chunks of rock and metal, called planetesimals, crashed into each other constantly, sticking together, growing larger. Some became the size of moons, some became the size of planets, and they continued to collide again and again in a cosmic demolition derby that lasted millions of years. Mercury was one of these growing worlds. Scientists believe it started much larger than it is today. Perhaps it was similar in composition to Earth or Venus, with a thick rocky mantle surrounding a modest iron core. It might have been 2 or even 3 times more massive than the Mercury we see now. It was becoming a proper planet, one that could have looked very different from the tiny metal-rich world we observe today. But then came the impact. We do not know exactly when it happened. We do not know the size of the object that struck Mercury, though it must have been enormous. What we do know is that this collision changed everything. The impact was so violent, so catastrophic, that it stripped away most of Mercury's outer rocky layers. The mantle, the crust, everything that made Mercury similar to other terrestrial planets, was blasted into space. Some of it fell back to the surface. Some of it was captured by the sun's gravity and lost forever. Some of it might have eventually fallen to Earth or Venus, carrying pieces of Mercury's original body across the inner solar system. What remained was a naked planetary core, the iron heart of a world that had been torn apart. This is why Mercury is so strange today. Its iron core makes up about 85% of the planet's radius. On Earth, the core is only about 55% of our radius. Mercury is in essence a giant metal ball with only a thin shell of rock covering it. If you could cut Mercury in half, you would see this immediately. A massive sphere of iron and nickel, surrounded by a mantle only about 400 kilometers thick, and a crust so thin that in some places it might be less than 100 kilometers deep. This makes Mercury the second densest planet in our solar system after Earth. But Earth is much larger, and its density is enhanced by gravitational compression. If you corrected for that compression effect, Mercury would actually be the densest planet of all. It has more metal, proportionally, than any other planet we know. It is as if someone took a planet and stripped away everything except its core, leaving behind only the heaviest, most resilient parts. The evidence for this giant impact is written into Mercury's very structure. Computer simulations of planetary formation cannot produce a world like Mercury through normal accumulation alone. The numbers do not work. You need something violent, something catastrophic. The giant impact theory is the best explanation we have, and it fits what we observe. But the impact left other scars too. When we look at Mercury's surface today, we see one of the oldest landscapes in the solar system. The Caloris Basin, one of the largest impact craters anywhere, stretches across 1,550 kilometers of Mercury's face. It formed about 3.9 billion years ago, during a period called the Late Heavy Bombardment, when asteroids and comets rained down on the inner planets with terrifying frequency. The Caloris impact was so powerful that it sent shock waves through the entire planet. On the opposite side of Mercury, directly across from Caloris, the surface crumpled into a weird jumbled terrain that scientists call chaotic regions. The seismic waves from that single impact traveled through Mercury's core, converged on the far side, and literally broke the ground. And Mercury is small, incredibly small, for a planet. It is only slightly larger than Earth's moon. You could fit Mercury inside the Atlantic Ocean with room to spare. Its diameter is just 4,879 kilometers, compared to Earth's 12,742 kilometers. If Earth were the size of a basketball, Mercury would be the size of a golf ball. Yet despite its small size, Mercury has gravity, not much, only about 38% of Earth's gravity, but enough to hold itself together, enough to maintain a spherical shape, enough to clear its orbit of debris and officially qualify as a planet rather than a dwarf planet or asteroid. This gravity, weak as it is, has consequences. It means Mercury cannot hold on to an atmosphere. Any gases released from its interior or delivered by comet impacts are quickly lost to space, stripped away by the solar wind or escaping due to the planet's low gravity. It means that Mercury is exposed, naked to the radiation and impacts that constantly assault its surface. It means that Mercury is in many ways a planet without protection. But Mercury's large iron core has another effect, one that scientists did not expect and still do not fully understand. That enormous metal heart generates a magnetic field. It is weak compared to Earth's, only about 1% as strong, but it exists, and it should not, because for a planet to have a magnetic field, it needs a liquid metallic core that is actively circulating, creating what scientists call a dynamo effect. On Earth, this works because our core is still hot, still churning, still generating the magnetic field that protects us from solar radiation. But Mercury is so small, small planets cool faster. Mercury should have frozen solid billions of years ago. Its core should be dead. Its magnetic field should not exist. Yet it does, and that means something inside Mercury is still moving, still alive, still generating that faint magnetic pulse that Messenger spacecraft detected when it arrived at Mercury in 2011. This is the first mystery of Mercury, a planet that should be geologically dead, yet shows signs of activity, a world stripped down to its core, yet still holding secrets in its metal heart. But to understand why Mercury is truly extreme, we need to look at how it moves, because Mercury does not orbit the Sun like other planets. Its dance is strange, slow, and utterly unique in our solar system. If you were standing on Mercury right now, watching the sun rise, you would witness something that defies everything you know about day and night. The sun would climb slowly above the horizon, growing larger and brighter as it ascended. Then, inexplicably, it would stop. It would reverse direction and sink back toward the horizon. And after this brief retreat, it would rise again, continuing its journey across the sky as if nothing strange had happened. This is called a double sunrise, and it only happens on Mercury. It is one of the many consequences of the strangest orbital mechanics in our entire solar system. Mercury does not move through space the way other planets do. Its orbit around the Sun is not a neat circle, it is stretched into an ellipse, more elongated than any other planet. At its closest approach to the Sun, called perihelion, Mercury comes within 46 million kilometers of our star. At its farthest point, aphelion, it swings out to 70 million kilometers. This difference of 24 million kilometers might not sound dramatic, but it creates wild variations in how Mercury experiences the Sun's influence. When Mercury is at perihelion, the Sun's gravity pulls harder on it. The planet speeds up, racing through its orbit at about 59 kilometers per second. This makes Mercury the fastest planet in the solar system, completing an entire orbit in just 88 Earth days. Ancient astronomers noticed this swift movement and named it after the Roman messenger god who wore winged sandals. They had no idea how appropriate that name would turn out to be. But speed is only part of Mercury's strangeness. The real peculiarity lies in how Mercury rotates on its axis compared to how it orbits the Sun. Most planets spin much faster than they orbit. Earth rotates once every 24 hours, but takes 365 days to complete an orbit. Mercury does the opposite. It rotates very slowly, taking 59 Earth days to complete one full rotation, and it takes 88 Earth days to orbit the Sun. These numbers are not random. They are locked together in what astronomers call a 3 to 2 resonance. Mercury rotates exactly 3 times for every 2 orbits it makes around the Sun. This means that if you marked a spot on Mercury's surface and watched it face the Sun, you would have to wait through 2 complete Mercury years before that same spot faced the Sun again in exactly the same way. The result is the longest day in the solar system. From sunrise to sunrise on Mercury takes 176 Earth days. That is one Mercury day. Think about that for a moment. If you stood in one place on Mercury's surface, you would experience 88 days of continuous blistering sunlight. Then, as the sun finally set, you would endure another 88 days of absolute darkness and bone-chilling cold. Half a Mercury year in daylight, half a Mercury year in night. This 3 to 2 resonance happened because of tidal forces from the sun. Over billions of years, the sun's gravity tugged on Mercury's slightly uneven mass distribution, gradually slowing its rotation. On our moon, Earth's gravity has done something similar, locking the moon so that it always shows us the same face. But Mercury did not lock into showing the sun just one face. Instead, it settled into this 3 to 2 pattern because of its elliptical orbit and the varying strength of solar gravity at different points. When Mercury is at perihelion, closest to the Sun, the tidal forces are strongest. The planet is moving fastest in its orbit, but rotating at a constant rate. This creates a situation where, from certain points on Mercury's surface, the orbital motion temporarily overtakes the rotational motion. The sun appears to slow down in the sky, stop, move backward, then continue forward again, hence the double sunrise, or in some locations, a double sunset. There are two specific spots on Mercury where this effect is most dramatic. These locations are called the hot poles, though they are not at Mercury's geographic north or south poles. They are on the equator, at the 2 points that face the sun directly when Mercury is at perihelion. If you were unfortunate enough to be standing at one of these hot poles during perihelion, you would experience the sun at its absolute largest and closest. The temperatures there can reach 430 degrees Celsius, hot enough to melt lead, hot enough to glow. But Mercury's strange motion creates another phenomenon that puzzled astronomers for centuries. As Mercury orbits the Sun, its elliptical path itself slowly rotates. The point of perihelion gradually shifts around the Sun over time. This is called orbital precession, and it happens to all planets to some degree because of the gravitational influence of other planets tugging on them. In the 1800s, astronomers measured Mercury's precession very precisely. They calculated that Mercury's perihelion should advance by about 531 arcseconds per century based on the gravitational pulls from Venus, Earth, Jupiter, and the other planets. But when they observed Mercury over many years, they found something disturbing. Mercury's perihelion was advancing by 574 arcseconds per century. There was an extra 43 arcseconds that Newtonian physics could not explain. This tiny discrepancy haunted astronomers for decades. Some proposed that there must be another planet, even closer to the Sun than Mercury, whose gravity was causing the extra precession. They even gave this hypothetical planet a name, Vulcan. Astronomers searched for Vulcan for years. They looked during solar eclipses when the sun's glare would not blind their telescopes. They calculated where it should be, but Vulcan never appeared. It did not exist. The mystery remained unsolved until 1915, when Albert Einstein published his general theory of relativity. Einstein's equations described gravity not as a force but as a curvature of space-time itself. Massive objects, like the sun, bend the fabric of space around them. Planets move through this curved space, following paths determined by the geometry of space-time rather than by forces in the classical sense. When Einstein applied his new equations to Mercury's orbit, something remarkable happened. The equations predicted that Mercury's perihelion should advance by an extra 43 arcseconds per century, exactly the amount that observations showed. Einstein's theory explained what Newton's could not. Mercury became the first experimental proof that general relativity was correct. The tiny planet, so close to the sun's intense gravitational field, was moving through space-time in a way that revealed the fundamental nature of the universe. From Earth, we can only ever see Mercury during twilight. Because it orbits so close to the sun, it never strays far from the solar glare. Ancient Babylonian astronomers tracked Mercury's appearances with remarkable precision, recording its movements on clay tablets over 3,000 years ago. The ancient Greeks initially thought Mercury was two different objects, one that appeared in the morning and one in the evening, until they realized it was the same wandering star. Even with modern telescopes, Mercury is difficult to observe. It is small, It is close to the sun's overwhelming brightness, and it shows phases like the moon as it orbits between us and the sun. When Mercury passes directly between Earth and the sun, an event called a transit, it appears as a tiny black dot crawling across the solar disk. These transits are rare, happening only about 13 times per century. The last one occurred in 2019. The next will not happen until 2032. Mercury's strange dance, its elongated orbit, its slow rotation locked in resonance with its year, all of these create the conditions for the most extreme temperature variations in the solar system because Mercury has almost no atmosphere to distribute heat around the planet. Each part of the surface heats and cools based solely on whether the sun is shining on it or not. And with days that last 176 Earth days, the sun has plenty of time to bake one side while the other side radiates its heat away into the coldness of space. This brings us to the next aspect of Mercury's extremes: the temperatures, the fire and the ice, the contradiction that makes Mercury not just the closest planet to the Sun, but also one of the coldest places in the inner solar system. There are places in our universe where heat and cold exist in ways that seem impossible. Black holes surrounded by accretion disks that glow with million-degree temperatures, while their event horizons represent the ultimate cold of a place where even light cannot escape. Neutron stars with surfaces hot enough to fuse iron, while their interiors contain matter in states we can barely comprehend. But you do not need to travel to exotic cosmic objects to find temperature extremes. You only need to go to Mercury. When the sun rises on Mercury, it does not warm the surface gently like it does on Earth. There is no atmosphere to scatter and soften the light. There are no clouds to provide shade. The sun's radiation hits the ground directly and immediately begins heating the rocks. Over the course of 88 days, as the sun climbs higher in the sky and grows larger, the temperature rises steadily. By the time the sun reaches its peak, the surface temperature at the equator can reach 430 degrees Celsius. To put that in perspective, water boils at 100 degrees Celsius. Lead melts at 327 degrees. Zinc melts at 420 degrees. At Mercury's peak temperatures, the ground itself would glow if you could see it in complete darkness. Any organic material would instantly combust. Plastics would vaporize. Even some metals would begin to soften and deform. The sunlight on Mercury is intense beyond anything we experience on Earth. Mercury receives about 6.5 times more solar energy per square meter than Earth does. If you could somehow stand on Mercury's day side, protected from the heat, the sun would appear 2.5 times larger in the sky than it does from Earth. Its brilliance would be almost unbearable to look at. The landscape would be harshly lit with razor-sharp shadows, every crater and rock standing out in extreme contrast. But then the sun sets. Slowly over the course of many Earth days, it sinks toward the horizon, and as it disappears, something remarkable happens. The temperature plummets. Without an atmosphere to trap heat, without oceans or lakes to store thermal energy, Mercury's surface cools almost as fast as it heated up. The rocks radiate their heat directly into space. Within hours of sunset, the temperature begins to drop dramatically. By the time the sun has been down for several Earth days, the temperature at that same equatorial location has fallen below freezing, and it keeps falling. At the coldest part of Mercury's night, Temperatures can drop to minus 180 degrees Celsius. This is colder than anywhere on Earth's surface, colder than the coldest Antarctic winter night, colder than the polar regions of Mars. The same spot that was hot enough to melt lead during the day becomes cold enough to freeze carbon dioxide into dry ice during the night. This is a temperature swing of over 600 degrees Celsius. No other planet in our solar system experiences anything close to this. Venus, which is even hotter than Mercury during the day, has a thick atmosphere that distributes heat around the planet. Its night side is almost as hot as its day side. Mars has temperature variations, but nothing like Mercury. Even our moon, which has no atmosphere and experiences extreme day night cycles, only swings through about 300 degrees because it is farther from the sun. Mercury's surface is constantly expanding and contracting as it heats and cools. The rocks crack and fracture from the thermal stress. Over billions of years, this process has broken down surface materials into a fine dust called regolith, similar to what covers the moon. But Mercury's regolith has been processed even more intensely because of the extreme temperature cycles and the constant bombardment of micrometeorites and solar wind particles. You would think that with temperatures like these, with daytime heat that can vaporize metals and nighttime cold that can freeze gases, Mercury would be completely sterile, a dead world with no surprises. But here is where Mercury reveals its greatest contradiction. In the year 1991, astronomers using radio telescopes detected something unexpected. They were bouncing radar signals off Mercury's surface to map its topography, and in some of the polar craters, they found regions that reflected radar waves in a very specific way. The reflection pattern matched ice, water ice. At first, many scientists were skeptical. How could ice exist on the closest planet to the sun? But as more observations accumulated, the evidence became undeniable. Mercury has water ice, not just traces, not just a few molecules frozen onto dust grains, but substantial deposits, possibly meters thick in some locations. The key to this mystery lies in Mercury's axial tilt. Earth is tilted about 23.5 degrees relative to its orbital plane, which gives us our seasons. Mercury is tilted only about 2 degrees. This means that at Mercury's poles, the sun always stays close to the horizon. It never climbs high in the sky, and in deep craters near the poles, craters with high rims that block the low-angle sunlight, there are places that never see the sun at all. These permanently shadowed regions are cold traps. Without direct sunlight, they never warm up. They stay at temperatures far below freezing, perhaps as cold as minus 200 degrees Celsius, forever. And in these eternal shadows, ice can survive. The Messenger spacecraft, which orbited Mercury from 2011 to 2015, confirmed the ice deposits and mapped them in detail. The largest deposits are in craters near the North Pole, craters with names like Prokofiev, Kandinsky, and Tolkien. Some of these craters are over 100 kilometers in diameter. The ice fills the shadowed regions like frozen lakes that have never melted. But where did this ice come from? Mercury is so close to the sun that water should never have been able to condense here during the planet's formation. The most likely explanation is that comets, those icy visitors from the outer solar system, crashed into Mercury over billions of years. Each comet impact delivered water and other volatile materials. Most of this water was lost immediately, vaporized by the heat or broken apart by solar radiation. But some of it, the water that landed in or bounced into those permanently shadowed craters, survived. Even more surprising, Messenger discovered that the ice is not pure. It is mixed with and covered by dark organic materials, complex carbon based molecules similar to what we find in comets and asteroids. These organic materials give the ice a dark appearance and may help insulate it, protecting it from any scattered light that reaches the crater floors. So Mercury hosts both extremes simultaneously. Parts of its surface reach temperatures that would melt lead. Other parts, just a few hundred kilometers away, are cold enough to preserve ice and organic molecules for billions of years, day and night on the same world, existing side by side in a way that seems to violate everything we expect from a planet so close to the Sun. This duality makes Mercury a natural laboratory for understanding how materials behave under extreme conditions. Scientists study Mercury to learn about space weathering, the process by which radiation and impacts alter planetary surfaces. They study it to understand how ice can survive in unlikely places, which has implications for finding water on other worlds. They study it to explore the limits of planetary environments. But Mercury's extremes are not limited to temperature. The radiation environment around Mercury is equally hostile, equally fascinating. And it is this radiation, this constant assault from the sun, that shapes everything about Mercury's surface in its thin veil of an atmosphere. If you tried to breathe on Mercury, you would die instantly, not from the heat or the cold, though those would kill you too. You would die because there is nothing to breathe. Mercury has no atmosphere in any meaningful sense. When we talk about Mercury's atmosphere, we are using the word very generously. What Mercury has is called an exosphere. It is so thin that calling it an atmosphere feels like a lie. The entire exosphere contains less gas than a modest sized room on Earth. If you could somehow collect all the atoms in Mercury's exosphere and compress them to Earth atmospheric pressure, they would fill a volume smaller than a backyard swimming pool. The exosphere exists at the boundary between atmosphere and space. The atoms are so spread out that they rarely collide with each other. Each atom is essentially in its own orbit around Mercury, following ballistic trajectories like tiny satellites. Some atoms fall back to the surface, some escape into space. New atoms replace them. The exosphere is constantly leaking away and being replenished, a ghostly presence that exists only because of active processes continuously feeding it. What exactly is in this exosphere? The Messenger spacecraft measured its composition in detail, and the results revealed a strange mixture. Oxygen is present, not the oxygen we breathe bound together in O2 molecules, but individual oxygen atoms. Sodium is there, glowing with a distinct golden color when excited by sunlight. Hydrogen, helium, potassium, calcium, and magnesium have all been detected. Even water molecules have been found, though in incredibly tiny amounts. None of these atoms came from an original atmosphere. Mercury lost any primordial atmosphere billions of years ago, if it ever had one. The planet's weak gravity and the intense solar wind stripped away any gases that might have surrounded the young planet. What we see now comes from three main sources. The first source is the surface itself. When micrometeorites, tiny dust grains traveling at tremendous speeds, slam into Mercury's surface, they vaporize on impact. The impact energy is so great that it breaks chemical bonds and frees atoms from the rocks. These atoms are ejected into space, where they become part of the exosphere. This process is called impact vaporization, and it happens constantly. Mercury is bombarded by thousands of micrometeorites every day. The second source is the solar wind. The sun does not just shine light, it also releases a constant stream of charged particles, mostly protons and electrons, that flow outward through the solar system at speeds of hundreds of kilometers per second. When these particles strike Mercury's surface, they can knock atoms loose through a process called sputtering. The energetic solar wind particles hit surface atoms so hard that they overcome the bonds holding them in place and send them flying into the exosphere. The third source is radioactive decay. Mercury's rocks contain trace amounts of radioactive elements. When these elements decay, they produce helium atoms as a byproduct. These helium atoms work their way through the rock grains and eventually escape into the exosphere. Most of Mercury's helium probably comes from this process. Because the exosphere is constantly being created and destroyed, it changes. It varies with time, with location, and with the solar wind conditions. When Mercury is at perihelion, closer to the sun, the solar wind is stronger and creates more sputtering. During solar flares, when the sun releases bursts of energetic particles, the exosphere brightens and expands. When Mercury is farther from the sun, at aphelion, the exosphere becomes thinner and dimmer. Sodium creates the most visible part of the exosphere. When sodium atoms are hit by sunlight, they absorb and re-emit light at specific wavelengths that produce a distinctive yellow-orange glow. This glow is so bright that astronomers on Earth can actually see it with powerful telescopes. Mercury appears to have a faint tail of sodium extending behind it, blown away from the sun by radiation pressure and the solar wind, like a comet's tail but made of metal vapor instead of ice. The sodium comes from minerals in Mercury's crust. When surface rocks are vaporized by impacts or sputtering, they release sodium atoms that quickly become part of the exosphere. Some of these atoms escape Mercury entirely. Others fall back to the surface where they can be released again later. This creates a cycle where sodium is constantly being added and removed. Potassium behaves similarly to sodium. Both are alkali metals that are easily released from rocks and produce visible light when excited by the sun. Calcium and magnesium were more surprising discoveries. Messenger detected these heavier elements in the exosphere, particularly after solar storms. This suggested that intense solar wind events can excavate deeper into the surface materials, releasing elements that are normally bound more tightly in minerals. The oxygen in Mercury's exosphere is particularly interesting. Where does it come from? Mercury's rocks contain oxygen bound in silicate minerals, but it takes a lot of energy to free that oxygen. The most likely source is water ice in the polar craters. Solar wind hydrogen can react with oxygen bearing minerals to create water molecules or hydroxyl groups. These can then be broken apart by radiation, releasing oxygen atoms. Some of these oxygen atoms make it into the exosphere, where Messenger could detect them. Standing on Mercury, if you could stand there, you would not feel wind. You would not hear any sound. Sound requires a medium to travel through, and Mercury's exosphere is far too thin to carry sound waves. The silence would be absolute and eerie. The only motion would be the slow movement of your own footsteps kicking up dust that would follow perfect parabolic arcs back to the ground, unimpeded by air resistance. Without an atmosphere to scatter light, the sky would be completely black even during the day. Stars would be visible right up to the edge of the sun's glare. The horizon would be sharp and clear, with no haze or atmospheric perspective to soften distant features. Everything would appear in harsh, unfiltered sunlight with deep black shadows. The lack of atmosphere also means no weather, no clouds, no rain, no storms. Mercury's surface today looks almost exactly as it did billions of years ago. There is no erosion from wind or water, no weathering in the conventional sense. The only changes come from impacts and from the slow, patient work of solar radiation breaking down surface materials atom by atom. This makes Mercury fundamentally different from Earth, Venus, and Mars. Those planets all have substantial atmospheres that interact with their surfaces, that create weather patterns, that protect them to varying degrees from radiation. Mercury stands naked before the sun's onslaught. Every photon, every particle of the solar wind, every cosmic ray strikes the surface with full force. In this constant bombardment, this relentless assault from space has shaped Mercury's surface in ways that scientists are still working to understand. It has created features that do not exist on any other world. It has weathered the rocks into materials unlike anything we see on Earth. The radiation environment around Mercury is not just an absence of atmosphere, it is an active, violent process that has been sculpting this world for billions of years. Imagine a place where the sun does not just warm you, it tears you apart, where particles moving at a significant fraction of the speed of light slam into everything they touch, where radiation is not an invisible danger, but the dominant force shaping the landscape. This is Mercury's reality every second of every day for 4.5 billion years. The sun does more than shine. Deep in its core, hydrogen fuses into helium at temperatures of 15 million degrees Celsius. This fusion releases tremendous energy that works its way outward over hundreds of thousands of years. When it finally reaches the sun's surface, it explodes outward in all directions as light, heat, and something else, the solar wind. The solar wind is a hurricane of charged particles, protons and electrons torn from the sun's outer atmosphere, accelerated to speeds between 300 and 800 kilometers per second. At Earth, we are protected from this wind by our magnetic field and atmosphere. The particles are deflected around our planet, creating beautiful auroras when some manage to spiral down along field lines toward the poles. We are shielded. We are safe. Mercury has no such luxury. At Mercury's distance from the sun, the solar wind is more than 6 times stronger than it is at Earth. The particle density is higher, the magnetic pressure is greater, and Mercury's magnetic field, while present, is weak, only about 1% the strength of Earth's field. It creates a small magnetosphere, a bubble of magnetic protection around the planet. But this bubble is tiny. It extends only about 1.5 Mercury radii from the planet's surface. Earth's magnetosphere extends about 10 Earth radii. Mercury's protection is minimal. The solar wind particles that make it through this weak magnetic shield strike Mercury's surface directly. When a proton moving at 500 kilometers per second hits a rock, it does not just bounce off. It penetrates into the crystal structure of the minerals, It transfers its kinetic energy to atoms in the rock. It can knock those atoms completely free from the surface, sending them flying into space. This is sputtering, and it happens continuously across Mercury's entire day side. Over time, sputtering changes the composition of surface materials. The lighter elements are preferentially removed because they are easier to knock loose. What remains becomes enriched in heavier elements. The surface darkens. Mercury's surface is significantly darker than the Moon's, even though both are airless rocky bodies bombarded by similar micrometeorites. The difference is the intensity of the solar wind at Mercury's orbit. The darkening is so pronounced that scientists initially expected Mercury to be brighter based on its composition. The space weathering has altered its appearance fundamentally. But the solar wind is not constant. The sun has moods. It goes through an 11-year cycle of activity, from solar minimum when it is relatively quiet to solar maximum when its surface erupts with sunspots, solar flares, and coronal mass ejections. During a coronal mass ejection, the sun hurls billions of tons of plasma into space in a single explosive event. If one of these plasma clouds hits Mercury, and they do regularly, the solar wind pressure can increase by factors of 10 or even 100. Messenger observed several of these events during its time at Mercury. The spacecraft measured how the magnetosphere compressed under the assault, sometimes getting pushed so close to the surface that the solar wind particles reached the ground in regions that were normally protected. The exosphere would brighten dramatically as increased sputtering released more atoms. The sodium tail would intensify and stretch farther behind the planet. During these extreme events, something remarkable happens. The magnetic field, lines connecting Mercury's day side to its night side, can break and reconnect in different configurations. This process, called magnetic reconnection, releases enormous amounts of energy. It accelerates particles to even higher speeds and creates what scientists call substorms in Mercury's magnetosphere. These are not storms in the meteorological sense. They are electromagnetic disturbances, reconfigurations of the magnetic field that channel particles toward the surface in specific patterns. The radiation is not just from the solar wind. Cosmic rays, high energy particles from exploding stars across the galaxy, also strike Mercury. On Earth, our atmosphere absorbs most cosmic rays before they reach the ground. On Mercury, they hit the surface with full force. When a cosmic ray, sometimes just a single proton, moving at nearly the speed of light, strikes a rock on Mercury, it can shatter atomic nuclei and create cascades of secondary particles. This process, called spallation, slowly changes the isotopic composition of surface materials. Scientists can measure this effect in meteorites that originated from Mercury, if we ever find any, or through remote sensing of nuclear reactions happening in real time on the surface. Messenger carried instruments that could detect neutrons and gamma rays produced by these cosmic ray interactions. The data revealed that Mercury's surface is constantly undergoing nuclear transformations at a microscopic level. There is another form of radiation affecting Mercury: ultraviolet light from the sun. At Earth, our ozone layer absorbs most of the harmful UV radiation. Mercury receives the full spectrum of solar UV, and at much higher intensities. UV photons have enough energy to break chemical bonds in minerals. Over time, this photon bombardment can alter the structure of surface materials. a process called photon-stimulated desorption. Molecules are broken apart, atoms are excited into higher energy states, and then released from the surface. All of these processes together, the solar wind sputtering, the micrometeorite impacts, the cosmic ray bombardment, the UV radiation, they create what scientists call space weathering. Mercury is the most space weathered body we have ever studied in detail. Every square centimeter of its surface has been processed and reprocessed countless times over billions of years. The evidence of this processing is visible in Mercury's spectrum. When MESSENGER analyzed the light reflecting off Mercury's surface, it found that the rocks appear much darker than they should based on their composition. The darkening is caused by the creation of nanophase iron particles. These are tiny grains of metallic iron, often just a few nanometers across, that form when solar wind ions break down iron-bearing minerals. The metallic iron is opaque and darkens the surface, even though it makes up only a small fraction of the material. This same process happens on the Moon, but on Mercury it is far more intense. The combination of stronger solar wind and higher temperatures accelerates the formation of these nanophase metals. Mercury's surface regolith contains more of these dark particles than lunar soil does. But space weathering creates another feature that is unique to Mercury: bright patches scattered across the surface, particularly around certain craters and in regions with unusual compositions. Messenger discovered these features and called them hollows. They are irregular depressions, sometimes just tens of meters across, sometimes several kilometers wide, with bright interiors that stand out against the dark surrounding terrain. Hollows are forming today. Right now, scientists know this because hollows appear on top of crater floors that are already space weathered and darkened. They are fresh features, geologically speaking. Some may be less than 1 million years old. Some might be forming at this very moment. The leading theory is that hollows form when volatile materials buried just beneath the surface are released by the constant radiation bombardment. Mercury's rocks contain small amounts of elements like sulfur, chlorine, and other compounds that can sublimate or be broken down by solar radiation. Over time, as these materials escape, they leave behind pits and depressions. The freshly exposed material has not yet been darkened by space weathering, so it appears bright. This means that Mercury's surface is actively changing, not quickly by human standards, but on geological timescales. Mercury is losing mass. It is slowly evaporating under the sun's assault. The atoms released from hollows and from sputtering across the entire surface are lost to space. Over billions of years, this process has removed layers of material from Mercury's surface. Some scientists estimate that Mercury may have lost the equivalent of a few meters of surface material over its history. That might not sound like much, but spread across the entire planet, it represents trillions of tons of rock literally vaporized by radiation. Mercury is shrinking not just from its core cooling and contracting, but from its surface being sandblasted away by the relentless particle wind from the sun. And yet, despite this constant assault, despite being the closest planet to a star that is actively trying to dismantle it, Mercury survives. It endures. And deep inside its battered, space-weathered crust, something is happening that no one expected. The planet's interior is not dead. It still holds heat. It still generates a magnetic field. And that magnetic field is one of the strangest puzzles in planetary science. In 1974, the Mariner 10 spacecraft made history as the first human made object to visit Mercury. As it swung past the tiny planet, its instruments began detecting something that mission scientists did not expect and could not immediately explain. Mercury had a magnetic field. This should not be possible, or rather, it should not still be possible. To understand why this is so strange, you need to understand how planetary magnetic fields work. Earth has a powerful magnetic field because deep beneath our feet, about 3,000 kilometers down, there is an outer core made of liquid iron and nickel. This liquid metal is constantly churning, driven by heat escaping from the even hotter inner core and by the planet's rotation. As this electrically conductive fluid moves through existing magnetic fields, it generates electric currents. These currents create new magnetic fields. The process feeds on itself in what scientists call a geodynamo. The result is the protective magnetic bubble that shields Earth from the solar wind. For this dynamo to work, you need several ingredients: a liquid metallic core, enough heat to keep it liquid and drive convection currents, sufficient planetary rotation to organize the fluid motion, and enough time for the process to stabilize. Small rocky bodies like asteroids and small moons do not have dynamos because they cooled too quickly. Their cores solidified billions of years ago. Any magnetic field they once had died with their internal heat. Mercury is small, very small for a planet. It is only slightly larger than our moon. Small objects cool faster than large ones because they have more surface area relative to their volume. Heat escapes more efficiently. By every reasonable estimate, Mercury should have frozen solid long ago. Its core should be a sphere of solid metal, and its magnetic field should have vanished billions of years before humans evolved to study it. Yet, when Mariner 10 flew past Mercury 3 times in 1974 and 1975, it measured a clear, global magnetic field. Not a strong one, only about 1% of Earth's field strength, but unmistakably present. The discovery was so surprising that many scientists wondered if the measurements were wrong, or if perhaps the field was a frozen remnant from ancient times, locked into Mercury's rocks like fossils preserve ancient life. It took more than 3 decades before we could test these theories. In 2008, the Messenger spacecraft arrived at Mercury for the first of several flybys before entering orbit in 2011. Its magnetometer, a sensitive instrument designed to measure magnetic fields, confirmed what Mariner 10 had found and revealed much more. Mercury's magnetic field is not a fossil, it is alive. It is being actively generated right now by some process deep inside the planet. The implications are profound. Mercury's core has not frozen solid. At least part of it remains liquid. Even after 4.5 billion years, something is keeping it warm. Something is driving the motion needed to generate the magnetic field. Messenger's measurements revealed other strange features of Mercury's magnetic field. Unlike Earth's field, which is relatively symmetric between the northern and southern hemispheres, Mercury's field is lopsided. The field is about 3 times stronger in the northern hemisphere than in the southern hemisphere. The magnetic equator, the line where the field switches from pointing down into the planet to pointing up out of it, is offset toward the north by nearly 500 kilometers. It is as if Mercury's magnetic field is tilted or shifted inside the planet. Why would this happen? On Earth, the magnetic field is generated throughout a large volume of the outer core. The geometry averages out to create a relatively symmetric field. Mercury's field, with its strange asymmetry, suggests that the dynamo might be generated in a thin shell of liquid metal at the top of the core rather than throughout its volume. The bulk of the core below might be solid or frozen into a rigid iron snow that does not participate in generating the field. This shell dynamo theory is supported by other evidence. Scientists studying Mercury's response to the Sun's gravitational tugs have measured how much the planet deforms under tidal forces. These measurements tell us about the internal structure. The data suggests that Mercury has a solid inner core about 2,000 kilometers in diameter, a liquid outer core shell perhaps 200 to 300 kilometers thick, and then the rocky mantle and crust above. That liquid shell is where the magnetic field is born. But this raises another question. What keeps that outer shell liquid? On Earth, heat from radioactive decay of elements like uranium, thorium, and potassium keeps the interior warm. But Mercury is so small and has such a large iron core relative to its rocky mantle that it should have very little of these radioactive elements. The heat source for Earth's dynamo should be largely absent on Mercury. One possibility is that Mercury's core is enriched in lighter elements, like sulfur. Sulfur mixed with iron creates an alloy that melts at lower temperatures and has different convection properties. As the core slowly cools and crystallizes, the sulfur-rich liquid might remain molten longer. The crystallization process itself releases heat and causes compositional convection as lighter elements are excluded from the solid iron and rise upward through the liquid. This could provide enough energy to sustain the dynamo. Another theory involves Mercury's elliptical orbit. As Mercury moves between perihelion and aphelion, the Sun's gravitational pull varies significantly. This causes the entire planet to flex and deform slightly. The tidal heating from this constant squeezing might add just enough energy to keep part of the core liquid. It is the same process that keeps Jupiter's moon Io volcanically active, though much weaker at Mercury. Whatever the exact mechanism, Mercury's magnetic field tells us that the planet is geologically active in ways we are still working to understand. The field interacts with the solar wind to create a magnetosphere, that small protective bubble we discussed earlier. But Mercury's magnetosphere is strange compared to Earth's. On Earth, the magnetosphere extends far into space, creating a long tail on the night side that stretches beyond the moon's orbit. Mercury's magnetosphere is compressed and small. During strong solar wind events, it can be pushed down almost to the surface. Messenger observed the boundary between the magnetosphere and the solar wind, called the magnetopause, fluctuating wildly in altitude. Sometimes it was 1.5 planetary radii above the surface. Other times, during intense solar storms, it compressed to just a few hundred kilometers above the ground. Inside this dynamic magnetosphere, Messenger detected populations of trapped charged particles, electrons and ions, spiraling along magnetic field lines, bouncing between the planet's poles. These particles come from the solar wind that manages to penetrate the weak magnetic shield, and from Mercury's own surface, knocked loose by impacts and sputtering. They form tenuous radiation belts, nothing like the intense Van Allen belts around Earth, but present nonetheless. The magnetic field also creates regions called cusps near the magnetic poles, where field lines connect directly to the interplanetary magnetic field. In these cusps, Solar wind particles have direct access to the surface. They funnel down along the field lines and bombard the polar regions with extra intensity. This might contribute to the bright radar reflections that led to the discovery of Mercury's polar ice deposits, though the connection is still being investigated. Perhaps most intriguingly, Messenger discovered evidence of magnetic anomalies scattered across Mercury's surface. These are regions where the crust itself has stronger magnetic properties than surrounding areas. They might be remnants from ancient times when Mercury's magnetic field was much stronger, or they might be melt rocks that cooled in the presence of the modern field and locked that magnetization into their crystal structures. Each anomaly is a clue to Mercury's magnetic history. Comparing Mercury's magnetic field to other planets reveals how unusual it is. Venus has no global field. Mars had a strong field billions of years ago, but lost it when its core froze. Earth maintains a powerful field because we are large enough to retain internal heat. Mercury, the smallest terrestrial planet, somehow still generates a field despite being so tiny. It defies our expectations. It challenges our models of planetary evolution. And this is just one of many ways Mercury refuses to be simple. Its surface is covered with features that took scientists by surprise when they finally got a close look. Cliffs that tell a story of a shrinking world, and ancient volcanic plains that should not exist, and those mysterious hollows, bright and fresh, forming even now under the sun's relentless gaze. If you could somehow descend through the darkness of space and land softly on Mercury's surface, the first thing you would notice, beyond the extreme temperature and airless silence, is how old everything looks. The ground beneath your feet would be ancient. The rocks would have witnessed the birth of the solar system. The craters stretching to every horizon would tell a story written in violence over billions of years. Mercury's surface is one of the oldest landscapes in our solar system. It preserves a record of the early days when planets were still forming and asteroids rained down in catastrophic numbers. The late heavy bombardment, a period about 3.9 billion years ago, when the inner solar system was swept by a storm of impacts, is written clearly into Mercury's face. The planet took hit after hit, and without weather or geological activity to erase the scars, they remain today almost exactly as they formed. The largest of these ancient wounds is the Caloris Basin. Imagine an impact so violent that it created a crater 1,550 kilometers across. That is roughly the distance from New York to Dallas. The asteroid or comet that created Caloris must have been at least 100 kilometers in diameter, moving at tens of kilometers per second. When it struck Mercury, the energy release was equivalent to trillions of nuclear weapons detonating simultaneously. The impact excavated a hole deep into Mercury's crust, throwing out ejecta that landed thousands of kilometers away. The basin floor eventually filled with lava flows, creating the smooth plains we see today. But the impact did more than create a crater. It sent shock waves through the entire planet. Seismic energy propagated through Mercury's interior, traveled around both sides, and converged at the exact opposite point on the other side of the world. At that antipodal point, directly across the planet from Caloris, the seismic waves met and interfered with each other. The ground shook so violently that the surface fractured and jumbled into a chaotic terrain of hills and valleys covering about 500,000 square kilometers. Scientists call these hilly and lineated terrain, and they are direct evidence that the calorous impact was powerful enough to damage the entire planet. No other world we have studied shows this effect so clearly. But impacts are not the only story written on Mercury's surface. Scattered across the planet are vast smooth plains. Early observers thought Mercury would look like the moon, covered entirely in craters with no large flat regions. Instead, nearly 40% of Mercury's surface is covered by these plains. For years, scientists debated their origin. Were they volcanic lava flows, or were they deposits of ejecta from giant impacts that melted and spread across the surface? Messenger settled the debate. The smooth plains are volcanic. They erupted from vents and fissures billions of years ago and flooded low-lying regions to depths of more than a kilometer in some places. The composition is similar to basalt, the same volcanic rock that forms Earth's ocean floors and erupts in Hawaii. But Mercury's volcanism was different from Earth's. On Earth, volcanic activity is driven by plate tectonics and the heat from radioactive decay. Mercury has no plate tectonics. Its crust is a single solid shell. The volcanism that created the smooth plains came from partial melting of the mantle, probably caused by heat retained from the planet's formation or released during the core's differentiation. The eruptions happened mostly between 3.8 and 3.5 billion years ago, relatively early in Mercury's history. Some volcanic features are more recent. Van Singer discovered what appear to be pyroclastic deposits, materials ejected explosively from volcanic vents. These deposits surround certain craters and vents, appearing bright orange in false color images due to their unusual composition. They contain volatile elements like sulfur, which is surprising because Mercury is so hot that volatiles should have been lost long ago. Yet somehow pockets of volatile rich material survived deep in Mercury's interior and erupted violently when they finally reached the surface. The most recent volcanism on Mercury may have occurred as little as 1 billion years ago, based on the low crater density on some volcanic features. This is far more recent than anyone expected. It suggests that Mercury remained geologically active far longer than its small size would predict. The planet's interior held on to heat and retained the ability to produce magma long after it should have frozen solid. But perhaps the strangest features on Mercury's surface are the ones that tell a story of contraction. Scattered across the planet are enormous cliffs called lobate scarps. These are thrust faults where one section of crust has been pushed up and over another section. Some lobate scarps are over 500 kilometers long and rise several kilometers above the surrounding terrain. They cut through craters and volcanic plains, showing that they formed relatively recently after most of the heavy bombardment had ended. These scarps tell us that Mercury has shrunk as the planet's interior cooled over billions of years. The materials contracted, the core solidified, or at least partially solidified, and took up less volume. The mantle and crust above had to accommodate this shrinkage. Unable to stretch or accommodate the change smoothly, the crust crumpled and fractured. Sections of the surface thrust upward along fault lines, creating the scarps we see today. Scientists estimate that Mercury's radius has decreased by about 7 kilometers since it formed. That might not sound like much, but spread across the entire surface, it represents an enormous amount of contraction. The surface area of Mercury has decreased by about 100,000 square kilometers. The entire planet is like a dried fruit, its skin wrinkling as the interior shrinks. This contraction has implications for Mercury's geological history. It likely shut down any volcanic activity by compressing the crust and making it harder for magma to reach the surface. It created stress patterns that might have influenced where hollows form today. It makes Mercury fundamentally different from Earth, where plate tectonics and mantle convection constantly recycle the surface and release internal heat. Walking across Mercury's surface, you would cross ancient impact basins, climb up lobate scarps that tower kilometers high, traverse smooth volcanic plains that once flowed like water, and encounter those mysterious hollows scattered in clusters around certain craters. Some hollows are bright blue in false color images, others appear golden. They pockmark crater floors and dot the central peaks of impact structures. Messenger discovered thousands of these hollows. They range from tens of meters to several kilometers across. They have irregular shapes, often appearing in clusters or swarms. Their interiors are bright and relatively fresh looking compared to the dark space weathered surfaces around them. Most importantly, they appear on top of features that are already ancient, meaning they formed recently, perhaps within the last few million years or less. The leading explanation remains that hollows form through the loss of volatile materials. Mercury's rocks apparently contain small amounts of elements and compounds that can sublimate or be destroyed by solar radiation. Over time, as these materials are lost, the rock becomes porous and collapses, creating the depressions we see. The process might be accelerated by Mercury's extreme temperature cycles, which can cause thermal fracturing and make it easier for buried materials to escape. But here is what makes hollows truly fascinating. They are forming now, right now, as we speak. Mercury's surface is actively changing in this unique way. The planet is not geologically dead. It is still evolving, still responding to the solar radiation and temperature extremes it endures. Every hollow is a window into active geological processes happening on a world we once thought was frozen in time billions of years ago. Mercury's surface is a library written in rock. Every crater is a page documenting ancient impacts. Every smooth plain records volcanic episodes. Every scarp shows the planet's slow contraction. Every hollow captures ongoing processes driven by the sun's relentless energy. And we have only just begun to read this library. Most of what Mercury can teach us still waits to be discovered. But to discover it, we need to go there. We need to send spacecraft capable of surviving the extreme environment, of mapping the surface in detail, of analyzing the composition of rocks and hollows and ice deposits. This is not easy. In fact, getting to Mercury is one of the most difficult challenges in planetary exploration. Getting to Mercury is harder than reaching any other planet in our solar system. This seems counterintuitive at first. Mercury is our closest planetary neighbor to the Sun. It is relatively nearby compared to the outer planets. You might think it would be easy to reach. You would be wrong. The problem is not distance. The problem is speed. Specifically, too much speed. When you launch a spacecraft from Earth, it already has Earth's orbital velocity around the Sun. We are moving through space at about 30 kilometers per second as we orbit. If you simply point a spacecraft toward Mercury and fire your engines, you do not fall inward toward the Sun. You stay in an elliptical orbit, similar to Earth's, because you still have all that orbital velocity. To actually reach Mercury, you need to shed an enormous amount of speed. You need to slow down by about 15 kilometers per second relative to your starting velocity. This is incredibly difficult. Rocket fuel is heavy, and you need exponentially more fuel to carry the fuel you need. A direct flight to Mercury with enough fuel to slow down would require a rocket larger than anything ever built. It is technically possible, but economically impractical. So mission planners use gravity assists. They fly the spacecraft past planets, using their gravitational fields like a whip to change direction and speed. Each flyby can add or subtract velocity without using any fuel, but getting the right trajectory requires patience and precise calculations. You might fly past Earth, then Venus, then Venus again, then Mercury, then Mercury again, gradually bleeding off speed with each encounter until finally, after years of travel, you have slowed down enough to enter orbit. This is what makes Mercury missions so rare and so challenging. Only two spacecraft have ever visited Mercury, and a third is on its way right now, following an incredibly complex path through the inner solar system. The first was Mariner 10, launched in November 1973. Mariner 10 used a gravity assist from Venus to reach Mercury, becoming the first spacecraft to use one planet's gravity to reach another. It flew past Mercury 3 times in 1974 and 1975, each time passing the same hemisphere because of the way its orbit resonated with Mercury's. Those three flybys mapped about 45% of Mercury's surface and discovered the magnetic field. The images Mariner 10 returned were revelatory. Scientists saw a world that looked superficially like the moon, but had features the moon did not have: the lobate scarps, the smooth plains, the strange bright patches. The data raised more questions than it answered. What was on the other 55% of the surface that Mariner 10 never saw? Where did the magnetic field come from? Was there really volcanism on this small planet? For more than 3 decades, those questions remained unanswered. No spacecraft returned to Mercury. The planet was simply too difficult to reach, and other destinations like Mars and the outer planets received more attention and funding. Mercury remained mysterious, tantalizing, a world we had glimpsed but not truly explored. Then, in August 2004, NASA launched the Messenger spacecraft. Messenger stands for Mercury surface, space environment, geochemistry, and ranging. The name is a nod to Mercury's mythological role as the messenger of the gods, and it was fitting because Messenger would carry messages from Mercury back to Earth for years to come. Messenger's journey to Mercury took nearly 7 years. The spacecraft flew past Earth once, Venus twice, and Mercury 3 times before finally entering orbit in March 2011. Each flyby was carefully planned to adjust the trajectory and shed velocity. The path was so convoluted that the spacecraft traveled more than 7.9 billion kilometers to reach a planet that is on average only 77 million kilometers from Earth at its closest approach. Once in orbit, Messenger transformed our understanding of Mercury. Over 4 years, it mapped 100% of the surface at high resolution. It measured the composition of rocks from orbit using instruments that could detect X-rays and gamma rays emitted when cosmic rays struck the surface. It characterized the magnetic field in detail, It discovered the water ice deposits in the polar craters. It found evidence of recent volcanic activity in those strange hollows forming on the surface right now. The spacecraft operated in an extremely harsh environment. At times, Messenger was close enough to Mercury that the sun's heat and the planet's reflected radiation raised temperatures on the spacecraft to over 300 degrees Celsius. To survive, engineers designed a massive sunshade made of ceramic fabric. This umbrella like structure kept the spacecraft's instruments and electronics in shadow, protecting them from the worst of the heat. Even with the sunshade, Messenger had to carefully manage its orientation and occasionally fire thrusters to adjust its orbit and prevent overheating. Messenger also faced the challenge of Mercury's gravity. The planet's gravity is weak, but the Sun's gravity is immense at Mercury's distance. Staying in a stable orbit required constant attention and frequent adjustments. Over time, Messenger's orbit decayed, bringing it closer and closer to Mercury's surface. In the final months of the mission, the spacecraft was skimming just a few kilometers above the surface at its lowest point, gathering incredibly detailed data about surface composition and topology. On April 30th, 2015, Messenger ran out of fuel. Without the ability to adjust its orbit, it succumbed to Mercury's gravity and impacted the surface at over 3.9 kilometers per second. The impact created a new crater about 16 meters across, adding one more scar to Mercury's already heavily cratered face. Messenger's mission was over, but the data it returned will fuel scientific research for decades. Even before Messenger ended, the European Space Agency and the Japan Aerospace Exploration Agency were planning the next mission to Mercury. Bepicolombo, named after Italian scientist Giuseppe Colombo, who helped plan Mariner 10's trajectory, launched in October 2018. It is the most complex planetary mission Europe has ever undertaken. Bepicolombo is not one spacecraft, but three. The Mercury Planetary Orbiter, built by ESA, will study Mercury's surface and interior. The Mercury Magnetospheric Orbiter, built by JAXA, will study the planet's magnetic field and its interaction with the solar wind. And the Mercury Transfer Module, which provides propulsion and power during the cruise to Mercury. Once at Mercury, the transfer module will be jettisoned and the two orbiters will separate into different orbits, each optimized for its science goals. Getting to Mercury is taking Bepicolombo 7 years, just like Messenger, but the trajectory is even more complex. The spacecraft will fly past Earth once, Venus twice, and Mercury 6 times before finally arriving in December 2025. Each flyby is precisely timed. If the spacecraft misses a flyby by even a small margin, the entire mission could be jeopardized. The navigation has to be perfect across billions of kilometers of travel. The engineering challenges are formidable. Bepicolombo has to withstand temperatures even more extreme than Messenger faced, because its orbit will bring it closer to Mercury. The spacecraft uses a combination of heat-resistant materials, reflective coatings, and active cooling systems. The solar panels can actually be tilted to reduce the amount of sunlight they receive when the heat becomes too intense. The main engine uses electric propulsion, which is more efficient than chemical rockets, and allowed Bepicolombo to carry less fuel. What will Bepicolombo discover when it finally arrives? We can only guess. It will map Mercury's magnetic field in 3 dimensions, revealing the structure of the dynamo deep in the planet's core. It will measure the composition of the surface with higher precision than Messenger, helping us understand exactly what Mercury is made of. It will study the hollows and perhaps catch them in the act of forming. It will search for evidence of recent geological activity. It will map the ice deposits in detail and analyze their composition to understand where they came from. There are already hints of discoveries to come. During its flybys of Mercury, Bepi Colombo has taken images and measurements. The spacecraft detected calcium and magnesium in the exosphere, elements that Messenger had also seen. It measured how the magnetosphere responds to different solar wind conditions. Each flyby provides a tantalizing glimpse of what the full mission will reveal when the orbiters begin their science observations in 2026. Looking beyond Bepi Colombo, scientists are already dreaming of future missions. A lander on Mercury's surface would be the ultimate challenge. The spacecraft would have to survive not just the journey to Mercury, but also the extreme surface temperatures. During the long Mercury day, a lander would need cooling systems powerful enough to prevent its electronics from melting. During the long night, it would need heating and power systems to survive the deep cold. Solar panels would work during the day, but provide far too much power, and they would be useless during the night. Perhaps nuclear power would be necessary. A lander could analyze rocks directly, measuring their composition and age, with instruments far more sophisticated than what an orbiter can carry. It could dig beneath the surface, where temperatures are more moderate and space weathering has not altered the materials. It could study how volatiles escape from hollows. It could search for seismic activity to determine if Mercury's interior is truly as active as the magnetic field suggests. Even more ambitious would be a sample return mission. Bringing pieces of Mercury back to Earth would allow scientists to study them with laboratory instruments that cannot be sent to space. We could determine the exact age of different surface features. We could measure isotopic ratios to understand Mercury's formation. We could analyze the composition of hollows and smooth plains and the mysterious bright deposits that might be recent volcanic materials. But sample return from Mercury faces all the same challenges as getting there in the first place, plus the difficulty of launching back off the surface and making the return journey to Earth. It would likely be the most expensive and complex robotic planetary mission ever attempted. Yet the scientific rewards would be immense. Mercury holds clues to the formation of our solar system, to how terrestrial planets evolve, to the limits of where rocky worlds can survive. Some scientists have proposed missions to Mercury's Lagrange points, stable locations where the gravitational pulls of Mercury and the Sun balance out. A spacecraft at one of these points could observe Mercury continuously and study how the exosphere and magnetosphere change over time. Others have suggested multiple small spacecraft that could be distributed around Mercury to create a network for monitoring magnetic field variations and mapping the gravity field with high precision. Every mission to Mercury pushes the boundaries of what is possible. Every discovery raises new questions, and with each answer, we learn not just about Mercury, but about planets in general, about how they form and evolve and survive in the harsh environments close to their stars. Mercury is a laboratory unlike anywhere else in our solar system, and we are only beginning to understand what it can teach us. There is something profound about Mercury's solitude. It orbits closer to the Sun than any other planet, bathed in light and radiation that would obliterate anything we recognize as life. It has no moon to keep it company, no companion world to share its endless journey. It rotates so slowly that each day lasts longer than two of its years. From its surface, the stars would be visible even at midday against a black sky, but you could never see Earth without a telescope. Mercury is alone in a way that is difficult for us to comprehend. And yet, this lonely world has so much to tell us. Mercury represents an extreme in planetary formation. When the solar system was young and planets were still coalescing from the disk of dust and gas around the newborn sun, Mercury formed in the hottest, most violent region. The giant impact that stripped away its outer layers was not unique. Earth likely suffered a similar impact that created our moon. Mars might have experienced catastrophic collisions that shaped its current form, but Mercury lost more than any other planet. It was reduced to its core, its essence, stripped of everything except the most resilient parts. This makes Mercury a window into planetary interiors. On Earth, our core is hidden beneath 2,900 kilometers of rocky mantle. We can study it only through seismic waves and indirect measurements. Mercury's core is right there, barely covered by a thin shell of rock. When we study Mercury, we are studying core material, learning about how iron and nickel behave under extreme pressure and temperature, understanding how planetary dynamos work. The exoplanet revolution has made Mercury more relevant than ever. In the past 3 decades, astronomers have discovered thousands of planets orbiting other stars. Many of these exoplanets are what scientists call hot Jupiters, gas giants orbiting extremely close to their stars, far closer than Mercury orbits our Sun. Others are rocky super Earths in tight orbits where surface temperatures must be thousands of degrees. These worlds seem impossible by the standards of our solar system, yet they are common throughout the galaxy. Mercury helps us understand these exotic worlds. It shows us what happens to a rocky planet that endures extreme stellar radiation, the space weathering, the volatile loss, the way surfaces darken and evolve. All of these processes are amplified on planets even closer to their stars. Some exoplanets might have surfaces entirely covered in molten rock. Others might have been stripped down to their cores even more completely than Mercury was. By understanding Mercury, we build the framework for understanding planets we will never visit. Mercury also teaches us about resilience and survival. This tiny world has endured 4.5 billion years of punishment. It has been battered by impacts, scoured by radiation, baked and frozen in endless cycles. It lost most of its original mass to a catastrophic collision, yet it persists. Its core still generates a magnetic field. Its surface still evolves through hollow formation. It maintains ice deposits in its polar craters, despite being so close to the sun. There is beauty in this persistence, beauty in a world that refuses to be simple or dead or predictable. Mercury constantly surprises us. Every time we think we understand it, new data reveals something unexpected. The ice in permanent shadow, the recent volcanism, the asymmetric magnetic field, the hollows forming today. Each discovery reminds us how much we still do not know about even the smallest planet in our solar system. Ancient peoples watched Mercury's swift movements across the sky and wove it into their myths. The Sumerians associated it with the god Nabu, the divine scribe. The ancient Greeks thought it was two different objects, calling it Apollo when it appeared in the morning sky and Hermes when it appeared in the evening. They eventually realized these were the same object and kept the name Hermes, the messenger god. The Romans translated this to Mercury, and the name stuck. Those ancient observers had no idea what they were looking at. They saw a bright dot that moved quickly and appeared and disappeared into the sun's glare. They could not have imagined a world of temperature extremes, of ancient impacts and volcanic plains, of a magnetic field generated in a liquid metal core, of ice hiding in eternal shadows. They could not have known that this tiny wandering light would one day tell us secrets about planet formation and survival. Modern astronomy has revealed Mercury to be far stranger and more interesting than any myth. We have sent spacecraft across billions of kilometers to study it. We have built instruments that can measure the composition of rocks from orbit, detect magnetic fields 1% the strength of Earth's, map ice deposits in craters that never see sunlight. We have invested decades of effort and billions of dollars to understand this small, seemingly insignificant world. Why? Because understanding Mercury helps us understand ourselves. It helps us understand how Earth formed and why our world turned out so different. Earth could have been Mercury if the impacts had been different, if we had formed a bit closer to the Sun, if our planet had been hit by a slightly larger impact, or that stripped away more of our mantle. The differences between Mercury and Earth are not fundamental, they are circumstantial, the result of where we formed and what happened to us in those violent early years. Mercury also represents hope in unexpected places. The ice deposits in the polar craters are a reminder that even in the harshest environments, even on the planet closest to our star, water can survive. If ice can persist on Mercury, then perhaps it can exist in other unlikely places throughout the solar system and beyond. This has implications for astrobiology, for the search for life. Water is essential for life as we know it, and finding it in Mercury's shadows shows that the universe is full of surprises. The hollows forming on Mercury's surface right now tell us that geological activity does not require plate tectonics or active volcanism. A world can be dynamic simply because of the interaction between its surface and the space environment. This challenges our definitions of what makes a planet geologically alive. It expands our understanding of planetary evolution. As you lie there, preparing to drift into sleep, think about Mercury making its eternal journey around the sun. Right now, at this very moment, the sun is rising somewhere on Mercury after 88 days of night. The surface is beginning to warm. Space-weathered rocks are absorbing sunlight and starting to glow with heat. Solar wind particles are slamming into the day side, sputtering atoms into the exosphere. The magnetic field is flexing and reconnecting as the solar wind pressure changes. Somewhere, a hollow might be forming as volatile materials escape from beneath the surface. Mercury does not know we exist. It does not know that tiny creatures on a distant blue planet have sent machines to study it, have built models to understand it, have wondered about its mysteries. It simply exists, following the path that gravity laid out for it 4.5 billion years ago. It will continue to exist long after humanity is gone, orbiting the sun through its slow death and expansion into a red giant, perhaps eventually being swallowed by the sun itself in 5 billion years. But for now, we share the solar system with Mercury. We have the privilege of studying it, of learning from it, of being amazed by it. This tiny, extreme, resilient world has taught us so much about planetary formation and evolution, about space weathering and magnetic fields, about survival against impossible odds, about finding beauty and complexity in places that seem barren and dead. Mercury is the most extreme planet in our solar system, the hottest and the coldest, the fastest and the slowest, the most stripped down and the most mysterious. It is a world of contradictions, a place where nothing should exist, yet everything surprises us. It is a reminder that every world, no matter how small or seemingly simple, has stories to tell if we are willing to listen. And so we continue to explore. Beepa Colombo is making its careful way through the inner solar system right now, preparing to arrive at Mercury in 2025 and begin answering questions we have been asking since Mariner 10 first flew past in 1974. Future missions will follow, each building on what came before, each revealing new layers of Mercury's secrets. The journey is just beginning. Mercury has been waiting for 4.5 billion years. It can wait a little longer while we figure out how to reach it, how to study it, how to understand it. And when we finally unravel its mysteries, we will look out at the universe with new eyes, knowing that even the smallest, loneliest worlds have profound things to teach us about our place in the cosmos. For tonight, let Mercury's story carry you into rest. Let the extremes of fire and ice, of ancient violence and patient survival remind you that the universe is vast and strange and beautiful. Dim the lights. Feel the comfort of your blanket and drift into sleep, knowing that somewhere out there, a tiny world is dancing with the sun, enduring, persisting, waiting to share more of its secrets with anyone curious enough to seek them.